Okay, so the subject of these two lectures are n = 2 gauge theories which have exactly marginal deformations. Now, in the last week lectures and Grasmur lectures, you have explored the infrared properties of various n = 2 gauge theories. The starting point is typically a very specific UV Lagrangian, say a pure n = 2 supersymmetric gauge theory. And the purpose of the game is to understand the physics of the corresponding theory as you explore the moduli space of vacuum of the theory. So you explore the infrared properties of the theory. What I want to do today and tomorrow is to try to understand what happens if the theory in the ultraviolet also has some parameters you can tune. So I want to play around with theories whose ultraviolet description has a moduli space of parameters, of exactly marginal deformations. I want to understand what happens as you tune these parameters in the Lagrangian to explore this moduli space. Now, of course, for each point in this moduli space, you have a theory. You can still ask, what's the infrared dynamics of the theory as you explore its moduli space of vacuum? So everything that you learned last week and this week with Craig, it's sort of fibered over the parameter space, ultraviolet parameter space of the theory. And although it looks like this would add just one extra layer of complication, actually this sort of fiber structure is very constraining. And you can learn a lot both about the ultraviolet and the infrared of these theories by requiring the infrared description to be properly fibered. So this will be sort of the main theme of the lectures. Now, to give a better idea of what's going to happen, we can use as an analogy, although incomplete, what you've learned about the infrared theories. So in the infrared theories, you typically started with say the purest U2 theory. You had a very large, you had a parameter space of vacuum parameterized by some exactly marginal, not exactly marginal, sorry, by some holomorphic coupling, holomorphic order parameter, trace of phi squared, expectation value of some operator in the theory. And as you vary this expectation value you have various phenomena, and there is a very large region at large U bigger than some scale, where everything is weakly coupled, and you can do a very careful analysis. And then, starting from this analysis and using holomorphicity in U, you can start exploring the interior and fill in to get a complete description of the dynamics of the theory over the whole moduli space of vacuum. Now, you also saw in Edward lectures first and then yesterday lecture by Greg, that you have to pay a price as you go in. So in the weakly coupled region, you had some nice effective Lagrangian. Which was a function of the U1 degrees of freedom, a scalar field, a U1 gauge field. But as you went in, you encountered interesting singularities and monodromies. So that starting with your original Lagrangian and your original gauge coupling inside this Lagrangian, and going around some path in the moduli space of vacuum, you could come back to the same theory, but with the wrong description. So if you started with some from this point where there was an infrared coupling that was very weak, and you went around, analytically continuing the gauge coupling as a function of this holomorphic parameter U, you might end up with a gauge coupling which is actually very strongly coupled. And you need to go to a different dual description where this gauge coupling is again weak. So you get all sorts of monodromies where the infrared coupling is transformed by some electromagnetic duality. So you need to remix your electric and magnetic fields in the Lagrangian. You need to do this duality transformation. And really, what you end up with is is a sort of manifold of Lagrangian descriptions rather than a single Lagrangian description. So you have just patches in your moduli space. In each moduli, in each patch, you can give a simple Lagrangian description. But as you move from a patch to the other, you need to subject the theory to some electromagnetic dualities. You just cannot describe everything with a single Lagrangian. Now, this is sort of a reasonable analogy for what's going to happen in the ultraviolet, although the details are different. So we are going to start in some region of this parameter space where we dialed all the couplings to be very weak, so that the Lagrangian description we have, in the ultraviolet Lagrangian description that we have, is valid. There will be some corner of the moduli space where all the couplings are weak in some Lagrangian description. Then we start dialing some of the coupling to become strong. We pass through some strong coupling region where the physics is pretty murky. But we end up emerging in some new region where a new weakly coupled description of the theory is available in terms of some completely different degrees of freedoms. And then we keep exploring, moving along sort of the boundary of this parameter space, finding a lot of weakly coupled descriptions. And at the end, we sort of try to fill in, to just give a general picture of the whole parameter space as a collection of weakly coupled Lagrangian descriptions. Now, in favorable cases, in each of these weakly coupled regions, we really do find an actual Lagrangian to describe the theory. But in some more interesting situations, more exotic things can happen. So what I mean with the weakly coupled corner of a moduli space is simply a place where I can tune the couplings until I can tune all the couplings until I decouple a sufficient number of gauge fields. Okay, so in the original Lagrangian description, I had some gauge fields, I had some matter. If I tune all the gauge couplings to become very, very weak, I'm left with a free theory of gauge fields moving around and free matter. But at some other locations, it's perfectly possible that even after I decouple all the gauge fields, even after I have a sort of maximal set of free gauge fields going around, I'm still left with some irreducible blocks of very strongly interacting degrees of freedoms that just do not admit a Lagrangian description. And as you explore the parameter space for more and more theories, you sort of come to the conclusion that this exotic behavior where I have these strongly interacting degrees of freedoms is actually generic. And the exceptional cases are the ones where I do have a Lagrangian description. So, I mean, we sort of expect in general that maybe our habit of describing field theories through Lagrangians might only give us a partial picture of a bigger story. But for n=2 theories, you can make this statement rather concrete. You can really list a very large classes of n=2 field theories and just see that most of them do not admit a Lagrangian description anywhere in parameter space. But still, because the infrared physics is fibered nicely over this parameter space, you can sort of compute the infrared physics in some place where you do have a Lagrangian and transport it around. And as a result, you end up computing a lot of things, a lot of quantities in theories without a Lagrangian, something that, in a sense, you're not supposed to be able to do. So I think this is one of the reasons for which theories with a lot of supersymmetry, like n=2 theories, are interesting. Although they might not be realistic, they give you a window into phenomena which you just have no technical means to access at the moment for theories with less supersymmetry. And there is really an ongoing program to compute correlation functions or whatever quantities that have some weak sort of holomorphic dependence on the couplings in theories with no Lagrangians. And this leads to some of these connections that Nima was mentioning with two-dimensional conformal field theories. Now, before we can get a glimpse of this whole structure, of course, we need to understand the Winkley coupled corner very, very well. So we need to understand what does it mean to give an n equal to Lagrangian. So let's see, I think I still use this. I just use both backward. Okay, so what is the most general renormalizable n equal to supersymmetric Lagrangian? Okay. So it turns out that the answer to this question, the n equal to supersymmetry constrains you enough that you can actually answer this question. You've seen what are the basic degrees of freedom that you can find in an equal to theory. There are vector multiplets. And hypermultiplets. In an n equal 1 language, a vector multiplet is just a gauge multiplet together with a chiral multiplet in the adjoint. You probably cannot see this from there. And an hypermultiplet is a combination of two chiral multiplets in conjugate representations of the gauge group. And it turns out that n equal to supersymmetry constrains your Lagrangian so much that the only interactions are just supersymmetric partners of the gauge interactions. So once you tell me what's the gauge group, or better, which gauge groups do you have? And what are the matter representations? The general structure of the Lagrangian is determined. The only freedom that you have left is to just put some gauge couplings inside and some mass parameters, as we'll see shortly. Now, there is a particularly important interaction from an n equal 1 point of view, which is a superpotential. This superpotential looks like this. Ignore overall normalizations. I'm not caring about the precise factors. You can find them, for example, in the papers of Saberg and Witten in the references. But you get this structure. So here's some hypermultiplets. They sit in they carry some gauge indexes, and they carry some flavor indexes. Because in general, it allows the same representation to appear many times. There is a term where the flavor indexes are contracted, while the gauge indexes are contracted with the adjoint scalar field. The adjoint scalar field sits in the adjoint, so by using the structure matrices that represent the action of the gauge group over the matter fields, you can just write it as something which carries two gauge indices in R and in R bar. And then you have a mass term, where you contract the gauge indices, instead, and it sits sort of in the adjoint of a flavor symmetry group acting on these matter fields. Now, if the flavor symmetries will play a very important role for us. So now, clearly, this superpotential is invariant if I just rotate the index S and T at the same time. So in general, you pretty much always have some U and A, some U and I flavor symmetry. At least if Ri is a complex representation, which means that it's distinct from the complex conjugate. But if this representation is real or pseudo-real, so it can be identified with its complex conjugate, then you can also try to rotate together R, Q, and Q tilde. But because of these couplings, you don't quite get a full U-Chuan symmetry. You cannot just rotate them freely. If R is real, then the joint representation can be represented as antisymmetric matrices, because essentially the gauge group is a subgroup of SO Chu times the dimension of the representation. So the superpotential will have an phi ij, where the gauge indices are antisymmetric. And then you can put your, you can combine, if you combine, let me say this way, right? So if you combine Q and Q tilde and call them, I don't know, Q check. Then now you need something antisymmetric to combine the flavor indices. So you need some symplectic form. In terms of the original variables, I'm just saying something like Q tilde minus Q tilde Q. So you can do whatever rotations you want on this index S and T, but it must preserve this symplectic form. As a consequence, if the representation was real, the flavor symmetry is enhanced to USP, Chu, and I. So unitary transformations which preserve a symplectic form. Instead, if Ri is pseudo-real, then the adjoint fields can be written in a way that has symmetric indices. And then you need to contract the flavor indices with something symmetric. And your U2 and I rotations must preserve this symmetric form, which means that the flavor group is promoted to SO, Chu, and I. Now, it's worth mentioning, because it will play a role, that if the representation is pseudo-real, you can actually try to keep half of this matter content, sort of have one half hypermultiplet, so that you would have an SO Chu n plus 1 sort of flavor symmetry. This is always possible classically. Quantum mechanically, there are some possible issues. So there is an anomaly that was identified by Witten. Sometimes the determinant of fermions in the hyperinos, of the fermions in the hypermultiplets, can have a sign ambiguity under large gauge transformations, which makes the theory inconsistent. So sometimes you can do this, but not always. And when we can do it, I will mention it. So now, as I was saying, every time you have a ferrosymmetry, you can include the mass parameter in the joint of the ferrosymmetry. But initially, when we describe the ultraviolet behavior of the theory, we want to describe a theory which has exactly marginal couplings, which is conformal. So we start by turning off these mass parameters. Then later, you can turn on the mass parameters, give expectation value to order parameters, and describe the infrared physics of the theory. Now, how do I know if a gauge coupling is actually exactly marginal? So in n=2 theories, gauge couplings receive are renormalized at one loop. So there is a one loop beta function. There are no renormalization theorems that guarantee that there are no perturbative renormalizations besides the one loop one. Now you could quibble about the possibility of non-perturbative renormalizations of the gauge coupling. And as far as I know, more or less, the standard argument is that if you try to write down some beta function which just has instant non-corrections, no perturbative corrections, you sort of encounter all sorts of bizarre phenomena. But I'm not aware of a strong non-renormalization theorem that tells you that if the one loop beta function vanishes, then there is no renormalization whatsoever. But this would be an assumption, a working assumption in what we are doing. And in a sense, the best check is that it's a self-consistent assumption, meaning that you can then determine the infrared physics and everything is working properly with the assumption that the gauge coupling was actually exactly marginal. Now, essentially, so if you put no matter, the gauge theory is automatically asymptotically free. As you add matter, yeah.
What exactly is the assumption?
I'm not 100% sure, but I haven't found the precise statement that there are no non-perturbative correction to tau. For example, in your paper, it sort of hand-waved away saying that a lot of weird things would happen if that was the case. But I'm not sure if somebody has later proven a non-renormalization theorem for the gauge couplings. Also non-perturbative? Okay. Yeah. n=2. Okay. Maybe later you can I can look for the reference. So anyway, so as you add matter, the beta function becomes smaller, and the absolute value, and the theory becomes less and less asymptotically free. If you add too much matter, the theory becomes infrared free, and and you get, because there is only the one loop correction, you really get a Landau pole in the running of the gauge coupling. So if you put just the right amount of matter, you can make the one loop function vanish, and then if there are no perturbative corrections and no perturbative corrections, the coupling is truly marginal. So this is what the situation we are interested in. Now, what is this right amount of matter? For any gauge group, so for any gauge group G, you can take the representation to be the adjoint, and then the beta function vanishes. This gives you n=4 supersymmetry, actually. So if you do that, the hypermultiplets and the vector multiplets are in the same, can be rotated among themselves by some extra supersymmetries. So this is a very interesting case, but it's sort of not representative of the general physics of n=2 theories. Although you can add mass parameters for this and break n=4 supersymmetry back down to n=2. But another simple possibility is to take SUN gauge groups and put and add Chu and C fundamental flavors. So take the representation to be just the sum of Chu and C copies of the fundamental representation. So this will give you a flavor symmetry of U, Chu, and C. Now, there is a variation on the idea of fundamentals. You can also have situations where you have your gauge group with several unitary factors. And you can add a bifundamental. Now, if you do that, a bifundamental counts as N1 copies of a fundamental for this gauge group, and then 2 copies of this fundamental, for this gauge group. So you can take, if you have several unitary gauge groups, you can take several combinations of bifundamentals and fundamentals to get your beta function to vanish. There are some very simple examples. For example, they are typically described graphically as a quiver diagram, where you represent your gauge groups by circles, and the bifundamentals by lines joining them. Then here, for example, the gauge group in the middle has 2 bifundamentals, so each corresponds to n fundamentals. So in total, there are 2 n fundamentals, and this gauge coupling is exactly marginal. For the gauge groups on the sides, we can add n more fundamentals, which I will represent like this. In this way, all 3 gauge couplings will be exactly marginal, because each gauge group will have a total of 2 n flavors. So here, so again, what I mean here is that I have n copies of fundamental. I have a bifundamental, another bifundamental, and finally other n copies of a fundamental, where the index 1, 2, 3 labels which gauge group I'm talking about. So what is the flavor symmetry of this theory? I have U1 times U1, because each of these is a representation of the gauge group which appears once. And then I have UN at the 2 ends. Okay? Now, of course, you can generate many more examples like this by just varying the rank of the gauge groups and the amount of matter that you're putting. For example, you could draw something more interesting. So this is another example. This is SU2 with 4 flavors, this is SU3 with 6 flavors, SU4 with 8 flavors, SU5 with 10 flavors. So all the gauge couplings are marginal. Now, of course, you might wonder, why don't I draw something even more complicated, ramifying in all possible ways? But actually, if you're looking for what are the possible shapes of a graph for which you can put numbers at the nodes, with the condition that that all the numbers around the node add up to twice the number in that node, you'll find that the shape of the graph is pretty much constrained. And if you played around with the theory of Lie algebras, you can recognize that this is more or less the condition for having a Dynkin diagram, which means that your quivers your conformal quivers will always look like a sequence of gauge group, or maybe a sequence which bifurcates at the end, or both ends. Or maybe a loop. I mean, to be precise, you get this sort of affine linking diagrams if you have if you only have bifundamentals and no, sorry. No, okay, yeah, you can get both affine linking diagrams and linking diagrams. And finally, you get this sort of exceptional diagrams. 1, 2, 3, 4, something like this. Okay. Now, okay, so this is a very large class of superconformal theories that one might have fun studying. And each has a whole lot of gauge couplings that you can vary. There are other possibilities. Let me just erase this. You can get other classical groups. For example, you can get USP. Which needs 2n plus 2 flavors. Now, when I say 2n plus 2 flavors, I mean that the flavor symmetry, these are really 2n plus 2 copies of the fundamental. So the flavor symmetry is going to be SO 4n plus 4. Now, you can have SO 2 and C with 2n minus 2 flavors. And this actually allows you to make quivers of these other classical groups. You're alternating USP and SO. Where here, these are half hypers. You see I'm putting, for example, 12 half hypers, which are 6 hypers for this USB4. In particular, because they are half hypers, they have SO1 flavor symmetries, or O1. I don't remember. So they don't have continuous flavor symmetries, except for what you put at the end. But anyway, in today's lectures, we'll just restrict ourselves to unitary groups. And actually, for most of the lectures, we'll restrict ourselves to SU2 gauge groups, which enjoys kind of a special role because the fundamental representation of SU2 is actually pseudo-real. So SU2 gauge groups are a little bit exceptional among unitary groups. And this will allow us to play some interesting games. But anyway, the basic idea I'm trying to convey is that with a little bit of combinatorial work, you can really write a list of all possible Lagrangians, n equal to Lagrangians. It's a superconformal symmetry with only marginal gauge couplings. And as I was saying, one of the conclusions of this program is that there are many more n equal to theories out there than this finite set of Lagrangians. Now, let me now ask the main question for this lecture. So what are the most general n equal to superconformal field theories? I mean, n equal to Lagrangians with all marginal couplings. With gauge group, SU2 to some power. Okay, so before I continue, are there any questions? Okay, so let's write down some examples of a gauge theory, which is a true-gauge group, which has a marginal coupling. So we said the canonical example is SU2 with with an adjoint. And this is the n equal 4 supersymmetric gauge theory. Then you can take SU2 plus 4 copies of the fundamental. This is called an F equal to 4 SU2 because it has 4 flavors. This has SO8 flavor symmetry. This essentially exhausts everything that we can do with one gauge group. So let's move to 2 gauge groups. Okay. Well, of course, there is a trivial possibility of just having 2 copies of these theories completely decoupled. But let's ignore that. The next thing you can do is to have 2 bifundamentals between the 2 gauge groups. This is a close relative of n equal 4 superior Mills. In a sense, it's an orbit full of n equal 4 superior Mills. Another possibility is to just do the sort of linear quiver we were drawing up here, just with n equal to 2. What are the flavor symmetries of these theories? Well, here I have 2 bifundamentals. Now, so you have 2 copies of the same representation. Naively, that would tell you that you have a U2 flavor symmetry. But remember that because the fundamental of SU2 is pseudo-real, the product of 2 fundamentals is real. So the bifundamental representation is real. So if I have 2 bifundamentals, I actually have an SO4 flavor symmetry. Okay. Now, this SO4 is really an SU2 times SU2 in the sense that each of, well, right. No, did I say SO4? I mean USP4. Yeah, okay. This has an USP4 flavor symmetry because I was saying the bifundamentals are real. And if I have an I real representations, I get a USP flavor symmetry. Here, this was a very exceptional case because I had 2 copies of a bifundamental. Here is a more typical case. I have 2 flavors here that gives me an SO4. And here I have another SO4. And finally, the bifundamental field, because it's real, has an USP2 flavor symmetry. Now, SO4 is really the same as SU2 times SU2. And USP2 is also the same as SU2. So this nice theory has 5 SU2 gauge groups, SU2 flavor groups. Okay. Now, notice that, as I said, a bifundamental is the same as 2 fundamentals. What's going on is that to get a bifundamental out of a fundamental, you gauge one of the 2 SU2s, and the other one is left as a flavor symmetry. So let me be a bit more specific. Essentially, what I'm saying is that if I take Q into tilde each sitting in the bifundamental of two gauge groups, two SU2 gauge groups. I can combine them into single Q check, right, which carries this SU2, this USP2 index. So I have one index for the gauge group 1, one index for the gauge group 2, and then I have this flavor index. I had 4 plus 4 chiral multiplets in the n=1 language, which is 8. And just writing 8 as 2 times 2 times 2, which in particular means that these three indices play exactly the same role. Although in this case we gauge these 2, and we let the third one as a flavor symmetry. There is really no reason for which I shouldn't be able to gauge all 3 of them. So I can very easily write down a classical Lagrangian where this is gauged by gauge group SU21, this is gauged by gauge group SU22, and this is gauged by gauge group SU23. Now, you might worry because these are sort of half hypermultiplets. It's like I'm using the representation Q1 times Q2 times Q3 by itself. I'm not accompanying it with another copy of it, with a complex conjugate of it. But this is fine because the product of two pseudo-reals is still pseudo-real. So I can have a single copy of it. Now there could be quantum anomalies naively, but you see, from the point of view of this SU2, these are just two flavors. From the point of view of this SU2, these are just two flavors. So there is no anomaly under global gauge transformation for this SU2, or for this SU2, or for this SU2. So everything is fine. So the most general, we need some sort of a graphical way to describe this situation. So here I was representing a bifundamental by a single line. So let me represent this trifundamental by some sort of a junction. Now, each of these trifundamentals counts as two fundamentals for each of the gauge groups. A gauge group will be exactly marginal if it has 4 fundamentals. So it means that every gauge group must be coupled to 2 of these blocks. So, for example, SU2 and F = 4 will look like this. I take 2 of these blocks and I gauge them together. This SU2, this other theory, which I denoted first like this, can be represented. So here, this is a block of these hypermultiplets. This is another block. And this is another block. So I have 2 gauge groups. Let me put a little dot to remind you that there is a gauge group there. So here I have 2 gauge groups. And I have the 5 SU2 flavor symmetries, which I was mentioning up here. So this diagram makes clear what's the matter content, which matter is coupled to which gauge group, and it denotes graphically some of the flavor symmetry of the theory. Although sometimes there's sort of an exceptional flavor symmetry which you cannot see from the diagram. For example, we said that in SU2 and F = 4, there is still an SO8 flavor symmetry because there are 2 copies of these 2 fundamentals. In this diagram, you only see an SU2 times SU2 times SU2 times SU2 subgroup of that SO8. So what's going on is just that there is an SO4 times SO4 inside the full SO8 flavor symmetry. Each of these SO4 correspond to the 2 SU2s acting on 2 hypermultiplet, on 2 fundamentals. Okay, so now that we have this sort of graphical tools, nothing prevents us from building very complicated theories with SU2 gauge groups, which can look actually much more complicated than the ones that we're describing there, because I can do funny things. Of course, I can take, I can just make some complicated picture by using blocks where all three favor symmetries have been gauged. And furthermore, nothing prevents me from doing loops. So essentially, from every trivalent graph, gamma, I get a theory, T, labeled by this graph, and made with SU2 gauge groups and pre-fundamental matter. There is a couple of exceptional situations. So this one, for example, is nothing special. You see you have two blocks gauged together by two gauge groups. So you just join these two lines. The only exceptional case is what happens if I draw a picture like this. So what happens if I take two of these favor symmetries, I identify them and gauge them? Well, I just need to understand what happens when I decompose 2 times 2 times 2a. The product of two vectors of SU2, 2 spin 1/2, is a spin 1 plus spin 0. So there is an adjoint there. They're really the sort of two copies of an adjoint, the R plus R bar of an adjoint, plus a singlet that is not gauged. So this picture really represents SU2 and n equal 4 plus a floating singlet. But adding this singlet is important because it means that I can do something like this. See? This adjoint, from the point of view of this other gauge group, corresponds to 3 fundamentals. Sorry, 3 halves of a fundamental, which was a little bit problematic. But if I add another half a fundamental, I get 2 fundamentals, which I can gauge. So here I have a funny situation where I have a gauge, two SU2 gauge groups. This is coupled to a vector. The vector is a real representation, so it has an sp2 level symmetry, and then we gauge that. Okay, so this is going to be the playground of the rest of today's lecture and most of tomorrow's lecture. So let's discuss some of the properties of these theories. Now, of course, you may feel that we're just adding a lot of unnecessary complication. But the beautiful thing is that I was saying, just the consistency conditions that come from having this large family of theories allow you to draw very strong conclusions on each and any of these theories. So if you try to study one of these theories by itself, it's going to be hopeless. But if you study all of them together, it becomes easy. So what are the properties of this T gamma associated to some graph gamma with a bunch of external legs and some loops? So suppose that you have n external legs and L loop and G loops. But now, if you have no loops, it's a tree, and it's very easy to see to count the number of vertices and internal legs. And then every loop removes 2 external legs and adds an internal edge. So it's easy to show that you have SU2 to the 3G minus 3 plus n gauge group. In particular, that means that there are going to be 3G minus 3 plus n parameters, tau, gauge couplings. There are also going to be 3G minus 3 plus n order parameters for the infrared theory. Notice that these other parameters and the gauge couplings are intimately connected, which is going to be very important. If you want to change a gauge coupling, what do? You take your original Lagrangian and you add a prepotential term. So these other parameters are sort of dual to the small deformations in the UV parameter space.
Please, given G and N, do you have overlap? How many equivalent diagrams you can draw?
I can tell. If there are trees, there is some Catalan number. I don't remember what is the combinatorics for when you have loops. But a lot. Grows exponentially. Now, there is also a flavor group, flavor symmetry group. Essentially, there is a flavor, SU2 flavor for every external leg. And in particular, there are the mass parameters for this flavor group, which are other parameters that are important in the infrared. And it is worth mentioning for a moment that you see the column branch scalars and the mass parameters really enter the same way. You could see the mass parameters as, you can identify the mass parameters as the order parameters for some very weakly gauged gauge groups. This is also another piece of useful information. Okay. So now this is the playground. These theories, each is labeled by a graph. They had the same, if you fix N and G, they had the same gauge groups, the same flavor groups, but the way the matter is coupled is radically different for every theory. And well, I can sort of anticipate the conclusion that all the theories which are labeled by graphs with the same G and the same N are really the same theory, just in different regions of parameter space. So this is going to be giving us the weakly coupled cusps of some gigantic blob. And part of the question is going to be understanding how these local parameters near each of the weakly coupled regions can be patched together to describe this big parameter space. Now, to do that, we need to learn about S-dualities. So before we throw ourselves into this complicated world, we should understand the S-dualities for the simplest possible theories. So I guess the blackboard over there. So in the last 15 minutes, I guess. Right, questions?
How do the theory is superconformal if you are including mass parameters?
Oh no, indeed. If you turn them on, you break superconformal invariance. So as long as you want to be in the UV, you don't turn them on. Then when you want to move in the AR, you turn on the mass parameters and the order parameters. And there's going to be some interesting 3G minus 3 plus n moduli space of vacuum, which you want to understand. Fibered or this 3G minus 3 plus n dimensional parameter space in the UV. It looks pretty ghastly, but it's not that bad.
Does this construction generalize to the higher rank?
Yes, but it becomes harder. Very simply because there is no trifundamental. Well, we really used very strongly the fact that SU2 has pseudo-real representations, fundamental representations. If you try to write a guy with 3 SU3 indices, you can, but it's not identified with its complex conjugate. So it gives, you're forced to introduce twice as much matter, which then in turn essentially makes the theory right away not asymptotically free or conformal, but infrared free. So to go to higher rank, we will need to produce some better building blocks to work with than just free hypermultiplets. But thankfully, they will be given us for free by Argyres cyber duality, which is a variant of S duality for higher rank. Well, that's for SU3. And then you can try to enlarge the story to higher rank, other gauge groups, and it becomes a little bit more baroque. There is a useful way to describe everything in terms of a certain 6-dimensional field theory. And I might be able to mention something about it towards the end of the lectures, or in one of this sort of extra lecture in the evening. Okay, so S duality, at least the beginning of S duality. So let's take, again, n equals 4 SU2 gauge theory. This is really the canonical example of S duality. The way people started suspecting that this theory could have some interesting dualities in the parameter space was the observation that if you move in the Coulomb branch, your central charge function is uncorrected. So this is an exact result at whatever value of the gauge coupling tau. It's true at coupling, and then by holomorphicity, it's just true at strong coupling as well. What are the particles that move around in this Coulomb branch? Well, we have a W boson. Now we have n equal 4 supersymmetry, not n equal 2. So the multiplet of this W boson is larger than what you saw before. It corresponds to really a vector multiplet plus an hypermultiplet. It has 16 components. Because it started with 16 supercharges. This is half BPS. So it breaks 8 supersymmetries, which means that you have 2 to the 4th states in the multiplet. This has electric charge 1, magnetic charge 0. Okay? And at weak coupling, it's a relatively light particle. Has a mass A, absolute value of A. Now, then, at weak coupling, you can build classical solitonic solutions and do semi-classical quantization around them to produce more particles. For example, there is a monopole magnetic monopole. The magnetic monopoles, again, can be half VPS. They break 8 out of 16 supercharges. And so they sit in the same sort of multiplet as the W boson. But they have magnetic charge 1 and electric charge 0. Okay? Now notice that the magnetic monopole starts its life as a very heavy particle at weak coupling, of course, because it receives its energy from the classical action of the classical solution. There is a 1 over g squared in front of the classical action. Or here, in the central charge, there is tau. Remember the tau, which is more or less 1 over e squared plus theta I of e squared plus theta over 2 pi, goes to I infinity at weak coupling. So this magnetic monopole starts its life very heavy. But as tau goes to 0, meaning as the gauge coupling is made very, very large, the monopole becomes lighter and lighter. At some point, it becomes lighter than the W boson. So it looks a little bit nonsensical to think of the W boson as the fundamental degree of freedom, and the magnetic monopole as some derived notion. Instead, you can conjecture that maybe you can combine a sort of electromagnetic duality that you saw with Witten and with Moore, which exchange QE and QM, exchange tau to 1 over tau, minus 1 over tau. And you can combine these new gauge fields possibly with this magnetic monopole to make, again, an abelian gauge group. Now, that looks a little bit of a stretch. In a sense, it's a much stronger statement than the original electromagnetic duality. Electromagnetic duality is something you just do in the Lagrangian. You take electric field, magnetic field, and you exchange them. But here we are claiming that this magnetic monopole can combine with this new abelian field to give you a non-abelian gauge symmetry. And there is no symmetry in the non-abelian Lagrangian which permutes electric and magnetic field. So this is, if true, this is a very non-trivial, non-perturbative statement. Now, the first test that this might be true came out by looking at the full spectrum of monopoles and dions. So first of all, starting from this magnetic monopole and just quantizing the zero mode, which is charged under the gauge fields, you can get all sorts of dions with Q magnetic equal to 1 and Q electric equal to n for any integer n. If you work a bit harder, you can look at magnetic monopoles with charge 2 and argue that there should be dions for every odd electric charge. And so on and so forth. You can argue that there is a full spectrum of monopoles and dions for whatever magnetic and electric charge which are coprime. So the whole lattice of different particles. And in particular, with the help of another useful statement, is that there is no wall crossing for half VPS states in n equals 4 superior Mills, which means that this weakly coupled spectrum is actually the spectrum everywhere. And you see that you have a spectrum of BPS particles that there is actually invariant under exchanging tau with minus 1 over tau and electric and magnetic fields. More generally, the spectrum seems to be invariant under a generic tau goes to A tau plus B over C tau plus D. So the picture is that if you have this upper half plane where tau lives, you have a weakly coupled region where tau goes to I infinity, where the W boson is the lightest happy PS particle. Then you have some region as tau goes to 0, where the magnetic monopole is the lightest particle. But there is also another region where the dion as tau goes to 1, you see that the particle that has electric charge -1 and magnetic charge 1 will be light. Then there is another region at tau goes to 2. And then there are smaller regions, well, small, they're really all the same size, but in the picture look smaller, around tau equal to 1/2. Small, like you can draw lots of these circles, which are regions where you have some weakly coupled description, as tau goes to some rational number, P and Q, minus P over Q. So you have this variety of weakly coupled regions separated by these difficult regions where everything is strongly coupled. All the coupling is order 1, and you really don't know what's going on. And so there is no direct way to transverse from here to here. No known proof of S-duality from field theory, from four-dimensional field theory. All that you can do is to compute some quantities that depend holomorphically on the coupling and check if they can be really compared properly at all the different cusps. So for example, it was checked that the partition function of n equal 4 square Mills on certain manifolds gives you a modular form in tau, which is a function which is invariant or covariant under these transformations. There is really a very long list of well, maybe not that long. There is a list of possible checks of S-duality. Almost all involve holomorphic quantities or protected quantities. There is no other sort of check. And in a sense, I'm not even sure that we can hope for some checks of S-duality for quantities that do not depend holomorphically in the coupling. In the sense that when I say that there is this formula, I'm cheating a little. See, it's true that there is no renormalization of the coupling, but there is still some finite renormalization. So, for n equal 4 superior Mills, there is so much supersymmetry that there are really very natural renormalization schemes in which there is a tau and a sort of canonical definition of tau, and then I'm ready to believe that you have these sort of transformations. But a feature that would be entertaining when writing inequality theories is that it becomes harder to write this sort of formula. Just because when you write a formula like this, you have implicitly picked a certain renormalization scheme in this region and a certain renormalization scheme in this region. You might have made another choice, which would have given you a slightly different map. And because there is really no overlap between the two, there is a certain amount of freedom in how to parameterize each region. Anyway, we'll see that better. But if you see, here holomorphicity is helping a lot, but if you had a quantity that did not depend holomorphically in the coupling, it might be trickier to find a normalization scheme that really allows you to keep exploring down. So S-duality is proving S-duality is a rather difficult problem. But for the next lectures, I will just assume that S-duality is true for this theory. And I will study the S-duality properties of an F equal to 4. And from there, I would move to the more general theories, T gamma. Okay. Any questions?
Is it possible to give analysis
If you have only one, no. Because in a sense, as I was saying, if you only have one, you have an SO1 flavor symmetry. There is no adjoint. But you have two copies, then yes. No. That's true. Yeah, if you move away from 4 dimensions, then you can, you're right, you can do better than that. You're right. There are more stringent tests. And also, when you study the theory on S4, there are some correlation functions that can be computed. Correlation functions themselves are do not depend holomorphically on decoupling, but there is sort of holomorphic factorization where you can write them as an integral of products of holomorphic quantities. And then this gives you enough mileage to do checks of S duality for those correlation functions. But I think that the general. Okay.